So in the previous example, we looked at methanol formation by reacting hydroxide with methyl bromide. And we said that methanol forms quite readily, right? We said it's a second order process. That means to say that the hydroxide reacts with methyl bromide to form methanol, right? And then you've lost a little bit of this bromide that's in here. Now, one of the questions that you may be having right now, I know I did when I was in college, is why does this chemical reaction work? Why is this actually occurring here? And we could look at it really from a lot of different perspectives here. And that's what we're going to do in this problem. We're going to take a look at this from several different perspectives. And we're going to lean heavily on the computer modeling here to try to see if we can get a little bit of an idea as to what's going on. We're going to start our journey by looking at our friend Lewis acid-base theory. And what does Lewis acid-base theory basically tell us? If you're electron rich, you're negatively charged. And if you're electron poor, you're positively charged. And just like magnets, the negative end of a magnet reacts with the positive end of a magnet to form an attraction between them, right? That's really what Lewis theory is pretty much telling you right here. So how do we apply this to our particular molecule? So what we're looking at here is we have an electrostatic potential map for hydroxide. And we have it for methyl bromide, for methanol, and then for the bromide that's made as the byproduct in this case. And we use computer modeling to do this. So for those of you playing along from home, we just use the PM7 Hamiltonium in MOPAC to model these out really quickly. And then we normalize the color scale for all of them. But more to the point here, what's important to understand is that if we look at hydroxide, you'll notice that there's sort of this rainbow looking shape right here. And the rainbow is important because remember, if we see red in that electrostatic potential map, that is telling us that red is, like, think of the alliteration, red is electron rich. So that means it's partially negatively charged. You can kind of think about it from this perspective, right? And then we see the blue on the other side of the molecule. That's telling us that it's electron poor. Let's say I'm putting a whole bunch of charge here. Whoops. So red electron rich, blue electron poor. So why is methanol interested in wanting to react with methyl bromide? Well, think about how it sees methyl bromide. As a whole, according to the electrostatic potential map, this whole thing is what? It's almost like a little bit electron deficient. This is the way that it sort of sees it in this case. So you can kind of think about this from being somewhat electron deficient, right? Remember, electron deficiency is really what sort of an effect? It's really an electronegativity effect, right? And so since we're not really dealing with any electronegative atoms in methyl bromide, bromine's not an electronegative atom, you have to kind of think about the entire electron density as it relates to the hydroxide. And what hydroxide sees is a giant ball of partially positive charge. So what do you think is going to happen? That negative charge right there is going to be drawn to the methyl bromide. So there's going to be a necessary attraction. It's a lot like, you can kind of think about it here, just from a fundamental charge perspective here. If I take a partially positive charge, or I take a positive charge, and then I combine it, oops, let's fix that. If I take a partially negative charge, and I combine it with a positive charge, what happens? The two of them react with each other, and then there's an attraction that forms, right? So the negative charge binds to the positive charge, right? There's an attraction. So the two of these are necessarily attracted to each other. So this is one way of thinking about it from Lewis acid-base theory. And that is that we have an electron-rich side of the molecule is interested in the overall electron density, or electron deficiency, if you will, in methyl bromide. And you go, okay, well, I'm not stupid. Where's the partial negative charges that are in methyl bromide? Good question. It's probably actually within the internal portions of this. So it's actually probably in or closer into the bond there. You just have to remember a bromine is huge, right? And so it has a big old electron cloud, but a lot of that electron cloud might be pulled into the actual sigma bond between the carbon and the bromine. But nevertheless, there's still an attraction. Looking at it from this perspective, there is an attraction. Why is there an attraction? Hydroxide, the oxygen in hydroxide, is attracted to the electron density, or lack thereof, of methyl bromide's electron cloud. So that's one perspective to take a look at. Another perspective we could take a look at is this new thing. Probably have never seen this before. Maybe you have, I don't know. It's called frontier molecular orbital theory. I love this theory because it explains so much in chemistry here. But basically what it is it's an explanation for why bond formation actually occurs. So according to frontier molecular orbital theory, bonding often occurs when, I'm going to give you some vocabulary terms right now, the HOMO reacts with or interacts with the LUMO. Okay, so what do these mean here? I'm going to rewrite these out in colors specifically because I want to point out something here. Your HOMO is an acronym, is an acronym that stands for highest occupied molecular orbital. Occupied, that's the key. So that means you have an orbital within the molecule that has electrons in it. And so I'm using red in this case specifically because it is electron rich in this particular example. So what this is this is an orbital that's the highest in energy, so it's the most reactive, that contains an electron pair. Okay, and we're going to talk about what that means here in a second. The HOMO is interacting with the LUMO. So think about a LUMO as the molecular orbital that is basically an empty parking spot, right? So this is the lowest unoccupied molecular orbital, It's not truly positive, it just doesn't have any electrons in it, but it's the lowest energy orbital that's actually missing an electron pair. It's the easiest parking spot to pull into is kind of the way to think about this. Okay, so we can again lean on computer modeling to take a look at what the HOMOs and the LUMOs look like for both of these reactants really carefully here. And this is the data that we actually see here. So we have hydroxide on the left-hand side, upper left-hand corner here. We can actually have the computer compute what is the energy of this particular orbital. It's negative 2.0 electron volts. And then for methyl bromide, we have another HOMO over here. So this is negative 10.2 electron volts. We'll talk about what that means here in a second. And then in the LUMOs, so these are the parking spots that we have. So I guess we should kind of point this out here. What these plots are telling you is that you have lots of electron density here and here in this molecule, and you have lots of electron density here and here in this particular model. You also notice too, you may have a teeny little bit of electron density here, but that's not terribly important in this case. That's kind of what these structures are basically telling you. And then the computer can more or less calculate what is the energy of these particular molecular orbitals, whatever that's worth. Okay, LUMO. LUMO's giant parking spots, right? So let's take a look at what's going on here. So you can kind of think about a LUMO for hydroxide in this case, big old parking spots here. So you'll notice there's a big parking spot that's right here. That is, you could potentially put electrons there if you want to, according to this theory here. But more to the point, remember all the chemistry is happening at the oxygen. And so what you might want to think about is that you can kind of think about this as sort of like there's a parking spot kind of like right there. And then same deal with the methyl bromide. Remember, the methyl bromide is all about getting chemistry to happen at the carbon. So you're noticing here that you have kind of like a partial positive charge right there. It's not a true partial positive charge, but it's kind of think about it from this particular perspective. You have parking spaces there. Okay, so what do we use this information for? Like, that's cool that you can model out these pretty balloon-looking shapes, but who cares, right? Well, let's look at a couple different combinations of these, because this is really what frontier orbital theory is about. How does the HOMO interact with the LUMO? So we're going to look at our first example. Let me go ahead and wipe some of this out here. Our first example that we're going to take a look at is we're going to say, let's say hypothetically, we take this HOMO and we react it with this LUMO. What's going to happen? Well, let's look at the energetics of what's going on over here. So this is the hydroxide HOMO reacting with the methyl bromide LUMO. And so if we plot the two, energy values, you notice here you have your two. This is your lone pair of electrons that's right there. But if we plot the two energy values and then we take a look at the gap between the two of them, what do we notice about the gap? The gap here is equal to, well, let's just sort of see, just do a subtraction between the two of them, right? And so we find out that it's about, the absolute value is about 1.4 electron volts. Pretty small gap right there. Okay, what about looking at it from this perspective? So let's look at it from this perspective. What if we take methyl bromide as the electron-rich HOMO and then react it with hydroxide as the LUMO, as the electron-poor LUMO? Well, what do you notice here? So if we look at the hydroxide LUMO, look how high up it is. It's 15.8 electron volts. And then we have methyl bromide as the HOMO, very low, negative 10.2 electron volts. So we have to do a little bit of math to kind of see this. What is the gap between the two of them? Pretty easy calculation to do. All we do is 15.8, and then we just, what do we add? We're subtracting negative 10.2, so this is 0.2, and we see that the gap is equal to about 26.0 electron volts. And you say, okay, so who cares about this? Why is this so important? Well, think about it from this perspective. I like a basketball analogy here. So if I were paid $1 million to take a basketball and put it into a hoop, do I want, by the way, your LUMO is your hoop. Do I want my LUMO to be 1.4 feet off the ground? Or do I want it to be 26.0 feet off the ground? Which is the easier thing to do? You don't know the basketball. Do you want your hoop to be down here? Or do you want it to be way where it's really easy to get it in? Or do you want it to be way up here where it's really hard to get it in? The lower one, right? So this tells us something right here. This is, put a little heart by it, this is telling us something right there, that this is the arrangement that we want to see. We want hydroxide to serve, we want hydroxide's LUMO, the electron-rich species, reacting with methyl bromide. And so what this tells us, what frontier orbital theory really tells us is this. Who is donating the electrons in this case? Well, when we looked at our energetics, we saw that we want the hydroxide HOMO. And since HOMO is the HOMO, highest occupied molecular orbital, is where the electrons are, that's where the electron rich is. This is hydroxide. It's actually donating the electrons here. And so you go, all right, so who's receiving the electrons in this case? Well, it must be methyl bromide, right? So this is yet another way that we can look at it. Not only is hydroxide naturally attracted to methyl bromide's electron cloud, but we know that hydroxide is very electron rich and it wants to donate things into methyl bromide that is electron poor. Where is it adding? To put it into very plain terms for you, we used orange as our example here. This is where it gets kind of cool. These orbitals right here, one of them is going to want to add into that parking space right there. That's fundamentally what's happening in this case. All right, so we have one more theory we can take a look at here, and we can look at this really entirely from, it's not really a theory, but a thermodynamics perspective here. So we call this, and again, you learn this in Chem 2, but this is reaction enthalpy change, right? And so what this is the thermodynamic quantity that describes the heat that's gained or released as the reactants are turned into products in this case. And so you learn a little bit about it, you learn a little bit about the math behind this, but long story short, we can compute values, gas phase values for all of these different molecules and ions here and have the computer tell us what the heats of formation for each one of these are. And you go, okay, so why is that so important? Well, it turns out that if I apply this equation, and we don't have to worry too much about the equation, but if I apply this equation, what is it telling me? I take the total amount of energy from the from the products, and then I subtract it from the total amount of energy from the reactants. And something interesting starts to happen here. So let's just do that math really quickly. It's easy to do. We're going to take negative 49 kcal per mole. We'll drop the unit here because this isn't Gen Chem. And we're going to go ahead and add negative 58 according to the equation. Some of you guys may remember this from Chem 2. And then we are going to subtract the energy of the reactant. So this is negative 34 plus negative 8. All right, so let's do the math really quickly. I have my trusty calculator right here. 49 negative. I'm going to add 58 negative to that. And then I am going to subtract negative 34 and then negative 8. And so when you solve this out, oops, do this in black. When you solve this out, standard state, when you solve this chemical reaction out, what do you find out? It works out to negative 65 kcal per mole. Okay, and you go, well, what's so special about that? Who cares about this? You should care about this because This number right here, this negative value, is telling you that when you take hydroxide and you react it with methyl bromide, you lose heat. This is what's called an exothermic process. Chemical reactions like to proceed from high potential energy to low potential energy, just like all other processes. You take a bowling ball at the top of a building and you push it off the side. The bowling ball was initially at very high potential energy. You push it off the side, it falls onto the pavement. It's now at low potential energy. Well, chemical reactions do the same thing. We start off as very high in energy, highly reactive, and then we lose that energy to the surroundings. This is an exothermic process in this case. And so what does this tell you? Any reaction that's exothermic oftentimes is going to be highly favorable. So putting this all together, why does this chemical reaction happen? Number one, the hydroxide is naturally attracted to the methyl bromide, according to Lewis theory. Number two, frontier molecular orbital theory tells us that the electrons that are in hydroxide are drawn to the parking space that's in methyl bromide. And then we can also see, looking at it from a reaction enthalpy change perspective, that the reaction appears to be exothermic, which is a good thing. It's a very highly favorable process. So this is a very, very, very highly favorable reaction, and this is one way that we can go and